Okay, we're going to finish up a few examples of the continuity and discontinuity, and then we'll take a look at differentiability. So we had just finished part A, and we said the function has removable discontinuity at x equals 2, and that's where the hole in the graph is at the point 2, 3. Okay, graph number, or letter B. F of x is a piecewise function. It's 1 over x squared if x is not equal to 0, and 1 if x is equal to 0. You might recall that the graph of 1 over x squared looks something like this. It looks like you're taking the 1 over x graph and squaring it, so everything's going to become positive. So this is the graph of 1 over x squared, and it's y equals 1 at 0. Okay. So what type of discontinuity does this graph have? Well, we would say it has a vertical asymptote. But I'd say that more if this point wasn't here, but the y-axis does serve as a vertical asymptote for this graph. So we could call that infinite discontinuity. Okay, graph C. Now notice that graph C is a piecewise function, and it contains the piecewise function that we used in part A. All right, the graph for part A, remember, is the line x plus 1, except there is a hole in the graph at 2, All right, but now what they're saying is, in letter C, in this graph, oh, they've added the point 2, 1. 2, 1. So that is now on the graph. So this is now representing the graph for part C. Okay, what kind of discontinuity do we have? All right, here we have a jump in the curve. So we're jumping from a y value close to 3 down to 1, then back up to 3. All right, so this is non-removable. Remember, in part A, it was removable discontinuity because you could plug up that hole with a single point. But here it's not removable because there is a y value, and you can't move it up to the y value of 3. Okay, I'm not sure if you know what this function is. This is called the greatest integer function. And if you've seen it before, it looks like a step function. So the greatest integer, when you plug a value in, you get out the greatest integer less than or equal to the number you plugged in. So for example, what is the greatest integer of 2.3? It's the greatest integer less than or equal to 2.3, so that's 2. What is the greatest integer of 4.9? It's 4. Okay, how about some negative numbers? What is the greatest integer of negative 1.3? Well, the greatest integer less than or equal to 1.3 is negative 2. How about negative 7.1? The greatest integer less than or equal to this is negative 8. All right, so what this graph looks like is on the left, you have a closed circle. On the right, you have an open circle. So remember, if you plugged in 1.5, the greatest integer less than or equal to 1.5 would be 1. Okay, and going back the other direction to do some negative numbers. Okay, so this is also called the step function or the floor function. Okay, so there's a lot of jumping going on in this graph. So this graph has jumps in it. We call that non-removable discontinuity. Okay, I think that's the end of discontinuity, and now we're going to start taking a look at differentiability. So a function f is differentiable at a if f prime of a exists. So the slope of the function at x equals a exists. All right, it is differentiable on an open interval, a to b, or a to infinity, or negative infinity to a, or negative infinity. So just some interval, okay? If it is differentiable at every number on the interval. Okay, so remember, the definition of derivative required that we take a limit. Okay? Notice that a limit exists when the limit on the left equals the limit on the right. Okay, and remember, this is the slope of the secant, this little expression right here. So, or the slope of, the slope between 2 points, right, on the left and on the right. So we want to know that the limit exists on the left, the slope exists on the left and on the right, and the two slopes are equal. So think of it as slope on left equals slope on right. So for example, if we have a function, f of x, and it's just rolling along, and I want to know about the slope at this point. I'll call this 2. So f prime of 2, it does exist because the slope on the left, if you took a point just on the left and created the slope, and just on the right, those slopes are approaching the slope of the tangent line. Okay, so the slope on the left and the slope on the right are the same. Okay, I'm going to make this graph continue and take a look at this point. Okay, if I were looking at the slopes on the left, I would say they're very big negative numbers. Negative, big. Slope. That's on the left. But on the right-hand side, I would say my slopes are positive and very small. You know, it looks close to 0 almost. So here, the slope on the left, you know, this could be negative 100, and the slope on the right, positive 1/2. Well, the slope on the left and the slope on the right are not the same. And so here at this point, f of x is not differentiable. So if this happens to be at x equals 5, we'd say f prime of 5 does not exist. All right, the left-hand slope does not equal the right-hand slope. Okay, we call this a sharp point. And it doesn't matter how sharp or how dull. If the slope on the left is not the same as the slope on the right, it's called a sharp point or a cusp. Okay, so it could be very subtle. All right, even that is going to be considered a sharp point. All right, this might be -5 for the slope, but this might be -3 for the slope. Okay, I have no scale here, so it's hard to give some numbers, but the slopes are different. So again, it doesn't matter how dull. Okay, or it could be very sharp, like a absolute value graph. That is a sharp point. That's a dull sharp point, but still a sharp point. Okay, let's see what's next. So here we are. There are 3 common ways for a function to fail to be differentiable at a point. So we were just giving you some examples of, or I was giving you examples of the sharp point on the previous page. So here is a piecewise function, x squared if x is less than 2, less than or equal to 2. So here we go, x squared. That's the parabola centered at the origin. And we could say this continues, okay? And x minus 2 quantity squared for greater than. Okay, so that's going to I don't know that I like their graph. I think this should be x minus 4 quantity squared to match their graph. Okay, that will be better because it has to be centered at 4, 0. Okay, so these 2 graphs come together and they meet at the point 2, 4. Okay, notice the slopes on the left of 2 are positive and the slopes on the right are negative. That means that here at 2, 4, we have a sharp point. And f prime of x does not exist, or f prime of 2 does not exist. Okay, what would the derivative graph look like? So looking at the first parabola, it has a 0 here. It's going to have negative slopes to the left, positive to the right. Okay. It actually looks like this. I'll put an open circle here because it doesn't exist there. Okay, this graph also has the same kind of linear first derivative. I'll put an open circle here. Okay, so the red graph represents the derivative of f of x. Open circle, no value for the slope at x equals 2. All right, let's take a look at the second graph here, and then we'll have to go to a new video, I think. So we have y equals x squared again. For x less than 2, it's not equal to, 2 is not included in that domain. Then we have the point 2, 5. Then we have 10 minus x squared. So remember, 10 was up here, and this is a negative opening downward parabola. Okay, it would be like this, where this was up at 10. So we're just looking at sort of this piece of it out here. All right, it seems like it's not the right concavity, but we're going to pretend it's going downhill like that. Okay, so what's the derivative graph look like? Okay, well, this parabola has a positive line for its derivative. The slope of 5 is 0, and the slope here would be really big negative.